This is the screencast for section 8.4, example 3, using partial fractions with improper integrals. So we're going to evaluate the antiderivative from 0 to infinity of 2 dx over x squared plus 4x plus 3, or state that it diverges. Alright, so I have a fraction here, and it might occur a rational function. It may occur to you maybe use substitution, but the problem is there's no 2x, the derivative of the denominator here, to cancel out with. So I think I am going to use partial fractions. So I'm going to take the limit as b approaches infinity of the antiderivative from 0 to b. So b is still going to be infinity, it's just going to approach it with the limit. Now this will be 2 over, and I factored the denominator, dx. Well, now that means if I have 2 over x plus 3 times x plus 1, that means that rational function can be rewritten as some number over x plus 3 plus some number over x plus 1. Well, I'm going to find out what those are. If x equals negative 3, a would be negative 1. If x equals negative 1, b would be positive 1. Which then means I get to substitute in for a and b, negative 1 and positive 1. Now I can take those antiderivatives, and you may be asking, Ms. Larson, where did the absolute value go with natural log? Remember, we're taking the absolute value, or the integral of 0 to infinity, so only positives in the first place. So we actually don't have to worry about absolute value in just this situation. So now I'm going to do fundamental theorem part 2. So I'm going to take this expression and plug in b, and subtract that expression, plug in 0. Simplify a little bit. This first expression, I have subtraction of 2 logs, so I can take the natural log then of the first divided by the second. And then I still have a minus, the natural log of 1 is 0, and then we'll be adding, because distribute the negative, the natural log of 3. Now, as I start to think about what will happen as b approaches infinity, this is not a good situation, because I'll get infinity over infinity. And taking L'Hopital's rule here is a little tricky because of this constant. We don't want that constant to go away. So instead, what I'm going to do is I'm going to multiply the numerator and denominator by 1 over b. So that way, in my limit expression, I get the natural log of, that'll be 1 plus 1 over b over 1 plus 3 over b. And I still have the plus natural log of 3. But now as b approaches infinity, this expression 1 over infinity approaches 0, and so does 3 over infinity. So now I have 1 over 1, which is the natural log of 1, still plus the natural log of 3, which is then, well, natural log of 1 is 0, so it's just the natural log of 3. So the area under the curve of this rational function from 0 to infinity is the natural log of 3 units. Then now try problem number 13, says evaluate the improper integral or state that it diverges. Alright, so I'm looking for the antiderivative, this time of negative 1 to infinity, so a little bit before the y-axis all the way to the right to infinity, of still a rational function, looking to me like I'm going to use partial fractions. So I'm going to factor the denominator in that expression, and of course take the limit as b approaches infinity of the antiderivative from negative 1 to specifically b. Which means then that that rational function can be written as a number over x plus 2 plus a number over x plus 3. So I'm going to, if I found a common denominator, evaluate this expression. If x equals negative 2, a equals 1. If x equals negative 3, b equals negative 1. Which then allows me to plug in for a in this expression here, positive 1, and then also the same for b. Well, it'd be negative 1, which is why you have the subtraction sign right there. So now I'm going to take the antiderivative. This time we need to use absolute value because we do have some negative numbers in our antiderivative. Our lower bound, or lower limit of integration is negative 1. And then minus the natural log of, again, absolute value of x plus 3. So now I have an expression I can use the fundamental theorem part 2 on. So I'll plug in b first, and then I'm subtracting 2 logs, so I combine that into 1 log of the quotient of those 2 expressions. Minus, same thing, the quotient, now plugging in negative 1. So I'm going to simplify that right side a little bit, and that's just the natural log of 1/2 after the subtraction sign. Now here, again, as b approaches infinity, I get the natural log of infinity over infinity. I can't use L'Hopital's here because it's not the limit. The limit itself isn't infinity over infinity. I'm trying to take the natural log of infinity over infinity. So instead, I'm going to again multiply the numerator by 1 over b and the denominator by 1 over b, which then gives me an expression where as b approaches infinity, simplifies this expression. So I have 1 plus 0 over 1 plus 0, and of course still plus. Now I took this natural log of 1/2, which is really the natural log of 2 to the negative 1, put the negative 1 out as a coefficient, so I have plus natural log of 2. Now the limit as b approaches infinity of the natural log of 1. Natural log of 1 is 0 plus the natural log of 2, so it's just the natural log of 2 units. So the area under the curve of this rational expression from negative 1 to infinity is the natural log of 2.